In this video, we're going to look at another example of finding an area between two curves. And in this case, we've got several curves. It's not just two curves, but that's okay. We want to find the area of the region enclosed by y equals 1/4 x squared, y equals 2x squared, x plus y equals 3, and we're going to look at when this happens on the positive side of the y-axis, so when x is greater than or equal to 0. Okay, well, one of the things that we try to look at when we're finding areas or doing integrals in general is it easier to integrate with respect to one variable versus another, depending on a couple of things. One is, how are the functions presented to you? Do we have y as a function of x, or do we have x as a function of y? In this case, the way the problem is written, we have y as a function of x for two of these, and then for the third one, we can easily find y as a function of x by just subtracting the x over to the right-hand side. So the way the functions are presented to us in this case, we might think that it's easier to integrate with respect to x. Notice, however, as I move from left to right, my top bounding curve changes, right? Here, we've got the parabola 2x squared on top. Here, we've got 1/4 x squared on bottom. Once we hit this point of intersection, though, we have the line on top and the 1/4 x squared on bottom. So we know since the bounding curve changes, we're going to have to split the integral into two pieces. We'll have to do two different integrals to be able to do that with respect to x. So it might be worth a look to see, okay, well, can I do this with a single integral with respect to y? Is it easier to express the region in terms as x is a function of y versus y as a function of x? So that would mean, would we have the same right bounding curve and the same left bounding curve throughout? Well, no. In this case, we have the same problem, right? We have the line is on the right, and then the flatter parabola, if you will, is on the right. So we would still have to do two functions of y, two integrals with respect to y, if we were going to find this area with respect to y, if we decided to integrate with respect to y. So the way the region is described to us is not very helpful for determining which way to do the integral, because which variable we should integrate with respect to, I should say, because we're going to have to do two integrals either way. So since the functions were already presented to us in terms of x, let's just do everything in terms of x and integrate with respect to x. All right, so I need to find the x coordinates of these points of integration. So first we'll set the 2x squared equal to 3 minus x, go through the equation solving. We get 2 points of intersection. We're only interested for when the x is positive, so we're going to use the x equal to 1. That'll give us our upper limit of integration here. Putting the other parabola equal to the line, going through, solving your equation, you get two solutions again, but the only one we want is 2, because again we want positive x's. And this is definitely verified here over in the graph, right? We see x coordinate of 1, x coordinate of 2. All right, so we're going to integrate from 0 to 1. The top bounding curve is 2x squared. The bottom bounding curve is 1/4 x squared. And so we'll do top minus bottom there. Do the same thing from 1 to 2, except that our top curve changes to 3 minus x. All right, so simplify our integrands a little bit. Find our antiderivatives for each piece, and these are polynomials, so those are nice things to be able to integrate. Evaluate both of your integrals using the fundamental theorem of calculus. Do some simplifying, and you should find that the area is equal to 3/2.